mention it again. Anyhow, now today we want to talk about the strain, something totally new, the concept of the strain. Then we are going to talk about Hooke's law and relationship of determining the type of material under stress. And to do that, let's first go back again, discuss the scenario that we have so far is a two-force member under a tension or compression. That doesn't matter. I usually show it in positive mode, a tension mode. It can change. So this rod made of certain material has a length, has an area, cross-sectional area. Obviously, after you put this load in it, the load should be at the centroid of the cross-section in order to be axially loaded. Remember, that means pure tension or pure compression. We discussed that last time. Anyhow, obviously, this rod is going to go into a little change in the length. As you see me doing this, keep doing it. Of course, this is plastic, so you can see that it's being stretched. But if this was a still, I probably would not do it. 10 of us has to pull it in order to see. Of course, still you cannot see it because the deformation generally are very small. Everybody understand. You come to this, walk into this room, all this beam and column are going through the deformation. They go through the stress. They are going to go through the strain. Strain has something to do with the change in the length. Everybody understands. So we call it normal strain. So I'm going to define that in a minute. Nevertheless, L is the length of this rod. It's going to go through the formation of the delta. Delta is not a strain. Delta is the total, write it down, total change in the length, which could be positive. It means it is in tension mode, or it could be negative, means it is in, so rod can get larger or smaller as long as it is under tension or compression. So remember that we have the same relationship between P and sigma. This is something you have to notice. There is a difference between P and sigma, I'm sorry. What is P? The P is total load. Everybody understand. What is sigma? Sigma is the amount of load per unit of area. So look the way you're using it, think about what. When you say PSI or pound per square inch, you are eliminating the area, in other words. You are saying this much force per unit of area. So P is total load, write it down because if you use the same concept, you will see that's what I'm talking about. P is the total load applied to this rod. Sigma is the amount of load applied to 1 unit of cross-section area. Is that correct or not? Yes? So it's PSI. Therefore, delta is, I put that in the same level. Delta is the total change in the length. Epsilon, this is related, is the normal strain, write it down. And it is the amount of deformation per unit of length. Delta is the total elongation or shortening or total change. Epsilon is the amount of deformation per unit of length. So example, if L equal to 100 inch, delta is very minute. First of all, it's very small. Let's say that delta is 0.02 inches. Is that 100 inches length? Let's say that. Let's say the delta is 0.02 inch. Is that correct or not? Yes? What is the delta? Is this much. What is the epsilon? By definition, epsilon is the amount of deformation, not for 100 inch, only for 1 inch. That's what you've written down. The amount of deformation per unit of length. So what should I do? I should take the total deformation divided by length. So that's how the formula comes out. Is that correct? So epsilon, for the first, by definition, equal to delta over L. Notice if you have L equal to 100 inches and delta is 0.02 inch, you don't want the change for 100. You want the change for 1 unit of length, and that's what epsilon is. Did you understand the meaning of epsilon? Epsilon is the amount of deformation per unit of length. Is that so? It is 0.02 divided by by 100 by definition. Is that correct? So this is the first formula that you will see for a strain. So therefore, this, I'm going to erase it and put the new formula here. So here, normal, because first of all, this is normal strain. We have another strain for the tau. We talk about it later on, which is the elongation or shortening. The symbol for that is epsilon. And by definition, epsilon equal to delta over L. So if I measure the delta, all I have to do is divide that. If this goes this much for entire length, I want the amount of deformation for 1 unit. I have to divide that by the length. So that's the first definition. So epsilon equal to delta. Does it have a unit? No, it's a ratio. Everybody sees it's a length over length. So the unit of that is inch over inch, or millimeter over millimeter. We go with the smallest unit because epsilon is very small. So look at this example. This is a numerical example just for you to get. I don't need to do that. It's so obvious. So for this problem, epsilon of this rod is equal to what? It is 0.02 inch divided by 100 inches. Is that correct or not? Yes. So the number actually become very small number. It's got 0.0001234 inch over inch. Now, many of you also, the solution manual, they show it this way. But since you are going probably to take ME219 leg or going to the other classes, I tell you right now in advance, the unit of the epsilon is always very small. See how many zeros there? And then sometimes you have 4 zeros, sometimes you have 5 zeros. It's very difficult to show it that way. The unit of strain is always in micro. What's macro? 10 to the power of minus 6. So I appreciate if you change that to the following, equal to, put 2 more 0 there, so it becomes 200 micro. Micro being 10 to the power of minus 6, rather adding 0.000, which you make lots of mistake there. Actually, this is exactly what the system is. You go, you buy a car in America, your mile, your speed and everything is in kilometer. I mean, it's mile, I'm sorry. If you go to Europe, then everything is in kilometer. It's not in meter, it's in kilometer, 50 kilometer, or here is in mile. So if you go to the lab, you put an item there and you test that the machine says 350. It's not 0.00350. It says 350 in micro. Everybody, the machine always is it designed for showing you in micro? Everybody understand that? Like exactly your needle on your car will show it in mile. Is that understood? Yes, it doesn't show it in feet or the inches. So therefore, I appreciate, although they are not using it in solution manual, but or they do, I don't remember. I would appreciate that you always express epsilon, which is a small quantity always, because not visible. This is when you come into this room, you don't see this beam is going to go down, yes, or this column going down. It's so minute, it's in order of 0.0000. Everybody understand what I'm saying? So might as well express it in micro, which is 10 to the power of minus micro 6, not 4. Actually, I told you this before, I'm saying it again. The only number that we are using it, you should use it there, get out of math classes, because in math classes you use 10 to the power of 4 or 5 or 7 or 8. In engineering, we never use that. Only number that we are using is 10 to the power of 3, which is kilo, 10 to the power of 6, which is mega, 10 to the power of minus 3, which is milli, 10 to the power of minus 6, which is micro. This is the number. All your homework should be in this order. You will see later on the table. Actually, in your handout, there is a table, everything expressed in this format. No 10 to the power. Please, I don't want to see ever your result in 10 to the power of minus 4 or minus 5. Actually, there is no name for it. Everybody see that? Kilo and mega, that's the design for, that's for engineering work. Anyhow, that's beside the point. You don't see that in the being expressed that way in what I rather you do it that way. Anyhow, that's the definition of epsilon. Did you get it? Yes? But let's now talk about general definition. So if you want to talk about general definition, this is it. You have an item there. You will see somewhere this in your book probably. So there is a point A, and then you draw a line here between point A, B. That's the length of it before the formation. That's the same as the length, L. Is that correct? After the formation, you loaded this structure. Probably point B goes to point B prime. So what's B prime indicate that from this discussion we have? B prime, of course, is the delta. Everybody understand that. This is the general definition of epsilon. Epsilon is equal to, I put here a limit because that's how we do the math, of AB prime minus AB. Everybody see that? What is AB prime minus AB? That's the definition of delta. Everybody understand? Divided by what? Divided by L, which is the original length. Is that correct? Divided by AB. So if you see that in your book, do not panic. This is the same definition I used here. Yes, delta over L. So mostly we use it that, but that's the general. Why? Because epsilon from point to point may changes everything. The same thing actually can be said about the sigma as well. Last time I gave you sigma and everybody assumed sigma equal to force over the area, which is true everywhere. But there is a change that it is coming in future. In the chapter 1, the load was at the center of the rod, yes or no? The stress was uniformly distributed over entire section. So sigma was constant. Agreed or not? In all your homework, that one, this one as well, you will see that this is what we did last time. So this was the cross section, doesn't matter how the rod moved. The sigma was, if it is in tension mode, is uniformly distributed over that. Is it going to happen in future? No. From chapter 3 and on, this is not the system. This is only happen for the two force member, which is pure tension and pure compression. For example, this is a rod. I put it under bending. You see that? This is coming in future. But you will see that this rod is not under pure tension and pure. Look on the top, it looks like it is getting smaller. On the bottom, it may getting in larger. So on top, it must be in compression. On the bottom, it must be in tension mode. So if the cross section I have here is compression, here is tension, somewhere in between should be 0 too. So you are going from minus 10 to plus 10. Everybody understand that? So the stresses keep changing. So don't assume that the stress is always like what you saw in chapter 1. This is a particular scenario about the two force member, force being at the most important part, the force being at the center. If you change the force upper or lower, it's going to bend as well. Everybody understand? We discussed that later on in chapter 4. So we call it axially loaded member. So with that being said, if I want to define the stress in general, I have to take, because the stress here and here and here and here could change. Everybody understand that? So I'm giving you the general definition of a stress. It is in the book. You probably have read it or see it, but I want you to understand the difference that we are going to have. So if this is dA, or little area, and then there is a force here, dFn, n indicate that that is normal to the surface, because when you get it, the force here, you have to break it into 3 components, normal and tangential. Is that correct or not? Yes? So that part of force, which is perpendicular to that area, then we say again, sigma, the same definition. This is the general definition of sigma. Sigma become limit like that of delta Fn, n indicate is normal to the cross section, divide, again, that's the force, divided by area. The area is dA. Everybody see that? When dA goes to 0, because this has to become a point. Is that correct or not? When dA goes to 0. So this is the general definition of the strain, which is plus or minus. Again, this is plus or minus because there should be extension or there should be a shortening. Is that correct? Like sigma. Sigma could be plus or minus. But I'm saying that this sigma later on is going to change in the case of torsion or in the change of bending. This sigma, everything on the cross section is going to be different, variable, not constant. Anyhow, these are the little point here and there that we need to discuss. Now let's go to the idea of this Hooke's law, see what happened there. Now, in order to see what is happening there, I'm going to show the same rod again, but this time I'm going to put it in the vertical because I want to show you there is no difference when you do it vertically or horizontally. This is still a rod under an axial load of P. Again, means pure tension or pure, in this case, pure tension. Yes or no? And then this rod has a length of L and has a cross-sectional area. A could be any shape. So it doesn't matter if it's round or square or rectangular shape. Yes or no? Okay, there is, as soon as I put there, this rod is going to get elongated equal to delta. Yes. Then I can calculate epsilon. If I measure the delta, I can calculate epsilon. Yes or no? Epsilon equals delta over L for time being. Okay. Now, before I go do any analysis, what do you think the delta will be dependent on? Just don't use, if you have seen this class before, don't mention, let the new student bring their idea in. Because if you have taken this course, you already know what delta is dependent. You know to remember the formula. Everybody understands. What do you think the delta, why delta become larger or smaller? Can you tell me why? What should I change? Is it dependent on the load? Of course, yes. The more load I have, the more delta. So delta will be a function of the load, yes or no? What else changes the amount of delta? What do you think? What causes delta to be larger, or would it make any difference, the plastic or steel? So the type of material must be somehow there. This is something new. Is that correct or not? The type of material, the delta will be depend on the type of material. We'll discuss that so I put here material. What else? Come on, guys. I have a rod here, 5 feet, or I have 10 feet. The delta will be the same or will be different? Different. So which one? What will be depending? Delta will be depending on the length. That's right. So that's what I want you to come up. What else? There is still more. Would it make a difference if the rod is this diameter or this big? Would it make any difference or not? Yes, all of that is logical aspect of this problem. Yes or no? So therefore, it's very important to recognize that. So if I want to draw force versus delta, I have to worry about all of that. Yes or no? So we have to plot here. This is the plot. So I'm going to change it. Don't do it yet. Don't do it until I ask you to write it. If I decide to go P versus delta, I have all this variable to worry about. Yes or no? Type of material is one, so I have to plot this for different material. I have to plot it for different length. I have to plot it with different areas. So in order to eliminate this, at least L and A, L is the length, A is the area. Instead of the P, I'm going to use sigma. What's the sigma? This P is the total load. Sigma is the amount of load per unit of area. So I don't have to worry about A. Is that understood that? And instead of delta, I should use epsilon. What is epsilon? Is the amount of deformation per unit of length. So notice, in effect, I have eliminated that for time being for my graph. So my graph will be only dependent on the type of material. So if you have aluminum or you have steel or you have wood, you will get different graph. Everybody, let's look at it, see what this graph looks like, which is the most important graph. The whole engineering design is based on this graph, which is called Hooke's law. Okay. Now, look this is what we have. I put it here. I have sigma equal to force over the area, yes or no? Then I have epsilon, which is equal to what? We just gave it to epsilon equal to delta over L. Yes? Now, look, the more P you have, the more sigma you have. And the relationship is linear because A is constant. Is that correct or not? So you double the load, sigma become double. Here, the same thing. Since L is constant, the more delta you have, the more epsilon you have. Is that correct or not? So rather than doing P versus delta, I'm doing sigma versus epsilon, which we call it StressStrain Curve. This is the relationship between stress and strain, sigma versus epsilon. Sigma you already know from last week. Epsilon is the new material today's lecture, yes, which is the amount of change per unit of length, not total length. Total length is delta. Okay, now let's start from 0. If the P is 0, sigma is 0, delta is 0, epsilon is 0. Then I put here 100-pound load on the same method. So of course I'm going to notice a sigma And I'm going to notice a delta, which gives me epsilon, correct or not? So I'm going to plot that. Then I'm going to increase the load. I'm going to go to this point, this point, this point. That I'm calculating sigma. But when I have the P, I have the A, I can calculate sigma. Is that so? As I increase this, I will see that this going to be a line. Actually, it happened that all this point, this is by testing. It's not the result. When you do this testing, all the point will fall on a straight line, which is very important factor here. What does it mean? It means they are proportionate. Is that correct? So in other words, write it down. If it is a straight line, if the load double, strain doubles. Is that correct or not? Very important phenomena here. So it becomes a straight line with some angle here, very steep line. Of course, I will discuss that later. So we keep increasing the load. At certain stage, you have experienced that yourself probably. If you get one of these paper clips and open it up and do this several times, you see, first of all, the color is changing and it gets a little bit hot. Have you noticed that? When you touch it, it gets hot. So after you reach to the certain point, it seems the molecule of the material gets loose a little bit from each other, and suddenly you see a larger deformation. Suddenly this line, because from now on, see, it's proportional, it goes up and up and up. Suddenly it gives up, as if suddenly you have a large epsilon or large delta. That point becomes the most critical point for, we call it sigma yield, because the material has yielded and has lost his strain to a certain degree because it's become hotter. It becomes like putting some oil there between the molecule, and they are getting suddenly a stretch as a larger limit compared to what it was before. And it has another aspect of it, as we'll talk about it. And then, you see, by adding a little load, I see a larger deformation. At that time, we are saying that material went into the yield. At that, we don't never want to go beyond that point, because if I do that, I have ruined the structure material. Everybody see what I'm talking about. Therefore, it picks up a little bit. I'm going to discuss that again and again with you later on, but this is the essential part of it. This line, which is line OA, what is the characteristic of it? It is a straight line. So we call it elastic range. This is very important. Elastic range. All right, because after that, it yields. The molecules separated a little bit from each other. After a while, again, it gets a little bit stronger. At certain point, reaches to where it's going to break, and that point is sigma yield. But before it gets to the yield, it uses its flexibility. Everybody understand that? So in all your analysis, don't worry about sigma ultimate. You should never go beyond sigma yield, because then the material has lost its format. Is that look what happened here? This is very important. Notice every time you come to this room, all these beams, column, everything that is structurally there is going to go through the stress and the strain, because you are adding weight. Yes or no? If there is no permanent deformation here, if you come down here, the beam goes a little bit down, you don't see it. It's very minute. But you go out, it goes back to the original format. That means you are on this line. So you go up here to this load, you unload, you are back to here. Everybody see that? You go up, down, up, down. You've got that 10,000 times. Still no permanent deformation. When you did this clip, you do 10 times this, you get a permanent. It never goes to the original shape. Have you seen it? Because you have passed the yield point. Is that correct? So if you pass this point, sigma yield, so you come here by chance. Instead of 50 students here, that's why we have a limit there, then we have 200 or 300 for whatever reason, fire or something happened, just jump. There is a possibility of overstretching the stresses. So what happened there, you go to that point, still it is okay because you are under sigma yield. But the point is when you unload it, you come back, because coming back is parallel to this, everybody. And then you have this much permanent, write it down, permanent epsilon, permanent deformation in the system. So the system never goes back to the original length. So you don't want to do that, because if you repeat that 100 times, they're going to be augmented. Everybody understand that. And finally, every time you come here, this comes down 1 millimeter, which is nothing. But you come 10,000 times, that's a lot. Is that the next time you come in after 5 years, this beam should be 10 inches below where it was before. Is that the case? Obviously not. Is that understood what I'm saying? That you cannot have permanent deformation in the system. So the most important thing of this graph, that your sigma applied always should be less than sigma yield. You should never go beyond sigma yield, although sigma ultimate yield. That's one characteristic of this graph, that you should not go beyond sigma yield. The next one is the angle. The type of this angle that created here depends on the type of material. If you do this for aluminum or steel, you get different curve with different angle. By the way, this angle is very, very close to 90 degrees. I draw it that way because I want you to see it, but I will give you the number now. This actually is an angle. In general, physically, you can see that's the phi. Is that correct or not? In general, that tangent of that phi, which is what? Look at this triangle. Tangent of that phi, look at this triangle. This is sigma, and that is epsilon, which is equal to sigma over epsilon. We are going to call it E, or modulus of elasticity. That angle represents, write it down this way, that angle represents modulus of elasticity, which indicate what type of material there is. Obviously, E is representative of the type of material, remember? So when I write it here, now I can change that to the E, or modulus of. So different material have different modulus of elasticity. Obviously, it still has a larger modulus of elasticity than this plastic. Actually, that plastic is not good. That plastic is not elastic material. This is what it is really. From here to here, we are in the elastic range. When you passed it, you are on the plastic range. Everybody, and so we are always going to be, at least for undergraduate study, we are going, or undergraduate design, we are always going to be in the elastic range, which is on the portion, we call it proportional limit. Why proportional limit? Because sigma doubles, delta doubles, epsilon double. It's all linear. Everybody see what the meaning of linear is mathematically. So you just doesn't matter. Everything as you see is linear. P double, sigma double, delta double, epsilon double. Everybody see that. So it's a linear proportion. It's an elastic round, no permanent deformation. And this is modulus of elasticity. Now I give you a number to digest all of this. For example, if you look at ASTM A36, which is in the table, which is the standard steel we are using everywhere, and we are going to use that a lot. Most of my homework are about this material. So therefore, for example, sigma yield will be, actually that's what 36 is about, is 36 KSI, or 36,000 PSI. It means that if you put 36,000 pounds per square inch, that material is going to reach to the yield. It's become no use anymore. Is that understood? Because it's become, after that, it changes the everything. Is that correct or not? And look at the modulus of elasticity. Modulus of elasticity become equal to 29 times 10 to the power of 6 psi, because look at the unit here. Let's go back to the unit. Now, this is the new equation. You already have there. Now, notice from this curve, I got a new equation here as well. Everybody understand what happened? The relationship between epsilon, actually this curve is this spread and strain and modulus of elasticity. You should remember this. This curve is very important. Actually, if you come to 219 this morning, this afternoon class, I'm going to ask them, and I asked them last week too. I said, go back, read chapter 2, because every discussion about the more complex problem is about the relationship between stress and strain, which we call it Hooke's law as well. Is that understood? Yes, so this is the Hooke's law, relationship between the stress and the strain and modulus of elasticity. From this, again, look at this triangle, guys. I'm going to do that. Tangent of that angle, which is modulus of elasticity, E equal to sigma over epsilon, yes? Or epsilon, actually we write it like that. Epsilon from the same equation. If I change here, I bring epsilon here, E here, that's how we do it. Epsilon, this is another formula, equal to sigma over modulus of elasticity. So I appreciate you use. This is the definition. This is the what is came out from the Hooke's law. Is that correct? A stress-strain relationship. Now, can we calculate our delta now from this equation? Let's come to our first equation for the deformation of this rod. Remember, this is the curve applied to any structure, including this. Yes or no? If I know the modulus of elasticity of that material, now I can calculate delta. Look at that equation. Epsilon equal to sigma over modulus of elasticity. But what is epsilon equal to by definition? Epsilon equal to delta over L. Okay. Write it down. Delta over L equal to sigma. What is sigma? Last week. Sigma equal to force over area, right or no? So equal to P over A over modulus of elasticity. Yes? Okay, so what's delta equal to? Delta, I have to put L here. Is that correct or not? Yes, become this divided by E, but A comes to the denominator. Yes, so delta become PL over EA. Okay. As an engineer, you may forget your name, but you never forget this formula again. So I'll tell you this. This is the key for entire those homework, not this homework, next homework, next, this delta and similar deformation. This is along the calculation of the delta or change in the length, which could be positive, means tension, extension, negative means shortening. But look what we said earlier. Look at this formula that I put here. Look whether everything applied here. So you should not remember the formula. I would ask you to remember this. This is the logic. That's the formula. You may remember it today, and if you don't use it for a few weeks, you may forget it. Yes, I said you never forget it, because at least as long as you are in ME 218, you are not going to forget it. If you're going to become an engineer, you will never going to forget it. Everybody understand that. But look whether the same concept is applied there. Look at the more P you have, the more delta. Everybody see that? P become larger, delta become larger. The more L you have, the more. However, if the material is stronger, E is larger, yes or no? You get E larger, delta become smaller. So it's reverse, it depends on the modulus of it. Also the area, the larger the area, the less delta. You see, everything that you were thinking logically happened to, this is all true for every equation, for everything. So why do you want to attach yourself to the formula? Go forget about that, attach yourself to the concept and what you were feeling about it. Is that understood? So if you do that, then everything becomes easier for you. And when you do that, then your homework becomes easier. And the only way to do it, you are the first time taking ME 218, you need to practice that. The more you practice, you can be able to judge for yourself what is happening. Is that understood? Yes? So this is the formula, and I'm going to expand that. So this is the three formula we end up today. So this is for this week. Next quiz is all about that. Everybody understand that. So there's nothing else to add to that. Delta equal to PL over EA. I'm going to put a summation here, but I'm going to explain that later on, because the delta could be two-part item. Yes or no? All right? So all those problems is about that. Let's now go to some exercise to see what's going to happen. By the way, because I went a little bit slow here, I want you to stop me 20 minutes before the quiz. I'm going to give you a few minutes extra time. I don't want to go over. When it's 20 minutes before the time, let me know. Okay? It's right now there?
No, you have 14 more minutes.
Yeah, okay, I knew that. I hope. I want to do a couple of examples. Yeah. Everybody got the idea here what this curve is about. There are a lot more to it as we go along. I'm going to explain that too. But I would like you always start reading these pages. And you read these pages, there are more material there, more information there. And I want to read you read all about it. And also, if you understand only 30% of it, it's okay. Next time you read it, you see that I will explain again and again by bringing new material into the system. For time being, let's leave it at that. Go through an exercise of some example. Let's say this time we have a rod here. Okay, this is a rod. horizontal rod, long, 7 meter long, and then divided in 3 meter, 2 meter. So this is 3 meter, and here is 2 meter, and 2 meter. And then it is attached to a wall with a pin. And we talked about that last time. I'm sure by now, after you did all your homework, you realize that if you have a system like that, and there is a pin here, it's not going to stay there. Is that correct or not? Yep. This is a pin. And this is a fix. If this was fixed, it would stay there straight. But it is pin. Yeah, there is no moment resistance here. So it is start to rotate. Is that correct or not? Therefore, I have to pop it up by some column or holding it from top with something. Is that correct? In order to make it straight. So that's what we have done here. So here, I'm not showing the size of it. This is just symbolic. So there is a wire going, I call it wire 1, which is 3 meter long. One is enough, but in this case, I have 2 here. Then there is wire 2, which is 4 meter long, and this rod is being held in horizontal position with these 2 wires. Yes? Okay. And most of your homework are in this format, one way or another. Now we are going to put a P here for this. Since we are only talking about epsilon, so I'm going to stick to that, and I'm not going to give you the value of the P. But after I put the P there, this rod is going to change format, yes or no? I'm going to, first of all, assume this is rigid. Rigid means the rod, let's call it A, B, C, D is a rigid, therefore it does not bend or anything, yeah? So if I put a load P at the end B, what's going to happen to this rod? How is it going to change format of it? Is it going to go down like that? Because you have to check that in your problem. Is it going to look that, or is it going to go like this? Which one? This way. Everybody see what I'm talking about? Now, I hope to understand what. Do you know why you put A, at A is a pin, you put AX and AY? Do you know why you put AX and AY there? Yes? Why? Why do you put AX and AY there?
It can't move in the X and it can't move in the
That's what I want to know. You put AX and AY there because it is resisting against the motion of moving upward and horizontally. Everybody understand that? In a static, I teach a static that way. You put, if this is free to go, it's go. If I put a support here, it's no longer free to move that way. Yes or no? That's exactly the point. People do not see that, and I do odd sort of thing. You put AX and AY there because that point is not moving vertically and not moving, or therefore it stays on that place. But you don't put any moment there, it start rotating. So there is a rotation there. So everybody see what I'm doing. It's very important for all this next set of homework. Point A stays the same. So before the formation, it was like that. After, this is an exaggeration. Exert the form, because this is rigid, it does not bend, it becomes like that. Yes or no? Yes? So, or I put it here just for you to see. Now, after we did that, we have measured this length, and this length end up to be 11.2 millimeter. So ND has gone down because of that load P. That's a part of the problem given. So this is given 11.2 meter. This is point B, and that is point C. This is 3 meter, 2 meter, and 2 meter, okay? Now, we want to calculate epsilon in wire 1 and wire 2. What are the strain in wire 1 and wire 2? What's the answer? Is wire 1 a stretch? Is wire 1 become longer or getting shorter? Longer. So it is under tension. Yes, or is wire 2 under tension? Do you know how much? We don't know yet, but can we calculate? What do you think that B is? The point B, which was here, gone down to B prime. Yes or no? Point C now end up here. Is that correct or not? This was B here at the center. Now I'm showing only the center. What do you think this BB prime is? I used it earlier in the symbolic way. What's BB prime is? Is it epsilon or is it delta? Delta of what? Delta of wire 1. What is CC prime? Delta of y. These are the points that you have to pick up from each problem yourself. Yeah, you do it, you get exercise, you do it there. I do it once here or twice. You do it in your homework. Then any example look the same to you. Is that correct or not? You have to practice that. In every problem, there are different formats. So since this is being stretched, this is symbolic. This could be 3 meters. 3 meters is up to ceiling. Everybody understand that. This is very small, in order of few millimeters. Yes or no? But since this is a geometry problem, I can calculate this angle, or I can use similar triangle. This is given 11.2. So this over that is equal to this over that, similar triangle. Or you can use this angle. In solution manual, they use angle. I never use angle. I always use the ratio, everybody, because it's simpler. Yes or no? So I'm using similar triangle scenario to calculate BB prime. But BB, when I calculate BB prime, I don't care about BB prime. That is delta 1. That's the elongation of wire 1. As soon as I calculate that, I'm home free from there. Everybody see that? But you have to look at the geometry. You have to look at the system. You have to know how the system behave. In every different problem, different system. Everybody understand that? Yes? Okay. So BB prime equal to delta 1. Now I can calculate that. So BB prime equal to delta 1. Or let's use the ratio first. So that is BB prime delta 1 over this, which is 11.2 millimeter over millimeter, must be equal to this length. This length is how much? This length is 3 meter. Because it's ratio, you can use meter or 3,000 millimeters. So since this is millimeter, I'm using millimeter. 3,000 millimeter over entire length. Entire length is 2 and 2 and 3, which is 7. 7,000 anyhow. So therefore, delta 1 become equal to, delta 1 become 4.8. Obviously, should be less than that, 4.8 millimeter. This is less, and CC prime is a little bit more, and then at the end is 11.2 with the same ratio. Is that correct or not? Yes? So let's calculate delta 2 as well. So delta 2, which is this one. So let's call this one, I'm going to call it here. This is delta 1. This is delta 2. So this is delta of wire 1. This is delta of wire 2. Geometrically, I can calculate that because this was rigid and it does not bend. So in other words, this which was like that, it went like this. Everybody see that? So the wire become extended. This is a very simple problem. Delta 2 again over 11.2. This time I have to use this over the length, which is 5 meter over 7 meters. So it is equal to 5,000 over 7,000. And delta 2 this time become equal to, you can calculate that yourself. Delta 2 become equal to 8 millimeter exact. So 8 millimeter. Now that I have delta, delta is the total elongation of the rod. The question was, what is epsilon, or the amount of change in the length? Yes or no? Correct? So therefore, epsilon 1 is equal to delta over original length. Delta is 4.8 millimeter original length. We don't never add this to it because this is minute compared to that. Everybody understand that. This, we never add. Some people have, because remember the delta was divided by original length. Is that correct or not? So divided by 3,000. That's right, 3,000. So again, if you see in the book or in the solution, you know, 0.0000, do not do that. So this becomes 160 micro, and it is plus. Why it is plus? Because it is in tension mode. If it was in compression mode, you get some of your problem. The rod is in there. Wire cannot do that. But if it is a link, a metal could be in tension or in compression. That's only the difference there. So epsilon 1 and epsilon 2, of course, is equal to, yes?
I think you have different units for 11.2. You have millimeters and meters.
No, these are all in millimeter.
In the graph.
Oh, these are in meter. This is meter, 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 but this is in milli. Oh, up here, I'm sorry. That's 11 point. It cannot be 11 point. One of your homework, you come up with delta equal 11.2 meter. I have a question about that. That's obviously I didn't forgot to put an M there. Is that correct or not? Do you follow what I'm saying? That epsilon or various, actually this happened. Like sometimes I asked in ME29 to calculate the deflection in this beam, they come out with 5 feet. Oh, okay. The beam is coming. It is not reasonable answer. There is some mistake there somewhere. Yes? Exactly what you asked. Is that correct or not? Thank you. So epsilon 2 is become equal to how much now? Epsilon 2 equal to 8 millimeter over original length. Original length was 4,000. And this one become exactly 200 micro. Actually, now that I have epsilon and I have L, and maybe if I can, I don't have the sigma. Okay, we get that later on. So we can calculate what is elasticity, stress strain. Is that how much time do I have?
2 minutes.
2 minutes. Okay. I was hoping to be able to do some of this homework, but let me give you a hint. At least you should start doing the first few homework there, which is very simple. Now, this is the scenario, guys. Remember that, you need to write this down. If you want to do the homework, which you should, otherwise you will fall behind. Using this formula and that formula and that formula, I don't have to add anything else. You should be able to do all this homework. Everybody understand that? But you go there, you will find some difficulty somewhere. That difficulty, I would do it through the example here. Everybody, but the rest is very simple. The only thing you should worry about is this. If you have a rod like that, and there is a load here, I want you to understand there is a load here. Obviously, this could be different material. The cross section is different. So this point move forward, and that point move forward as well. So if this is A, this is the B, this is the C. You calculate delta 1. Delta 1 is how much point B move forward, yes or no? But I want to see how much C moves forward. I have to calculate delta 1 plus delta 2. So that's why I put here a summation. So delta, write it down. Anytime E changes or L changes or material or area changes, or P changes, you have to change it. Sometimes, like before, we put a P that way, 5 kips here, and maybe 2 kips there. Like this one is under 5 kips of tension. What is the AB under? 2 kips of compression. No. We did that last time. It's not under 2 kips of compression. On 3. Very good. Now we check that. This is misleading. This is not under 2 kips of the. You have to come up with the internal. Yes or no? Remember, the internal here is 3. Actually, 5 reduces, because if this was not there, this would have been 5 and 5. That 2 reduces that to 3. Use the idea that I presented to you last time. Is that understood? That you have to go with the internal forces. This is internal. Remember that. This is not external. Again, one more time. These are that normal forces that we were calculating in exercise 1. Okay, that by saying that, you should be home free. You should really be able to do that. Of course, I'm going to do 2, 3, 4 example next Tuesday. All right.